cheers. So, no, hello everyone. It's great to be here. Seems to be a long time. Whoops. Seems to be a long time since I did a COMET talk. I'm going the wrong way already. Okay, so yeah, it's great to be. Thanks for your wonderful introduction. And I've prepared a talk which is in these three segments, but it's also a bit of a story. So I'm going to start off by telling you a little bit about rock physics as a general laboratory tool and how I got into this business, going back a few years now. So deformation in the field, deformation in the laboratory, and what can we learn, what are the current challenges, and then move on to some older work on laboratory simulation of volcanic tectonics, and where does the pressure and stress go, and how can we detect it, how can we learn about the volcanic plumbing system as a consequence, and then finally some new results, recently published new results. Probably take up less than a third of this talk, but hopefully of interest to the COMET community. But it's a bit of a story behind this talk as well. So starting out from the beginning, rock deformation in the field. This is one example of many that you can pick up in the literature. This was published by Dan Faulkner and Tom Mitchell and others some years ago. And Dan and Tom were interested in looking at fractured damage zones in earthquake mechanics. So this is an example from Chile, from the Calato-Coloso fault zone. So you can see here we are in Chile on the right hand side. Here's the fault zone, and it's a very large fault zone. So it already gives a little bit of a challenge to your budding earthquake geologists or field geologists, and whereabouts do you go to look. Chile's a good example because it's quite well exposed. So Tom and Dan did publish a nice study here in Nature 2007, looking at the fracture damage as you approach the fault core. But it's not quite the same problem as you have on volcanoes. On volcanoes, at least you know where they are. They're smaller. And this is the volcano I've been working on for quite a few years now. This is an old picture from 2004, taken from the boat. Just took a boat ride around the volcano. It's a Stromboli volcano, 2004. And there are many, many models out there seeking to understand this very large flank collapse feature. You can see the Sierra del Fuoco on the side of the volcano, including this model published in 2005 by my longtime collaborator Sergio Vinciguerra. And it's a volcano I've worked on for many years. So a few years after that, here's another picture featuring the back of Richard Walker's head as he joined us on the field trip from the side of the Sierra del Fuoco, looking across to some boulders clearly just been falling down this slope from the dust. And then most recently, just a couple of years ago now, we got back just between two of the pandemic shutdowns. We managed to get over to Italy in 2019 to collect some new data, and this time looking from the other side of that flank collapse. So the last picture was over from this direction, and now we're looking from the other side. So it's a volcano which a lot of people have studied. We are just one of them. Most recently, we've revisited this problem, volcano-tectonics and flank collapse, by my colleague Tom Alcock, with a look of steely-eyed determination in his face here in this field work. And Tom is looking to map remote sensing data and back out fractured damage zones and map those on top of the larger scale features from the volcanic edifice itself. So we think there's a weakness zone going through the island. Here's the Sierra del Fuoco, plenty of dikes and other fractures, but most of the volcano, actually, the picture on the bottom right, is submarine. So this is in progress at the moment, and maybe even I can convince Tom to give you a talk about his research in another year or two. So watch this space. Of course, I have to mention hazard at this point. No talk on this kind of topic is complete without mentioning the huge hazard large volcanoes pose to the population, especially when they're near large cities. So this is a classic example. City of Naples, flanked on one side by Vesuvius, and then the other side by Campi Phlegrae, and we'll come back to talking about Campi Phlegrae and the nested caldera system at the very end of the talk. But here is a good example of why these things are very important. Lots of work goes on at the INGV to model what may happen. So modelling a pyroclastic flow going down the side of Vesuvius. Pompeii used to be over here, I believe, and I think that's all we need to say. But eruption forecasting, of course, is a big challenge for us all, and remains so. A simple model of a volcano-tectonic driven volcanic hazard, something like this: a slug of magma arises, accommodated by the edifice, starts to swell and fracture. The fracturing generates seismicity. The pathways for fluid and gas movement gives us some geochemical indicators, and in this case, from Pinatubo, the increasing number of earthquakes per day can be used to generate a proxy or forecast for the eventual time of eruption, with the important caveat that this sort of simple analysis of the seismic events per day only really works for volcanoes that have not erupted for quite a long time. That is to say, volcanoes with a long repose interval. And there are plenty of colleagues working on this, such as Chris Kilburn, Andrew Bell and others, and I'm not going to dwell on that other than to say that the seismic response of active volcanoes is something which has been interesting to me for a very long time, and for this reason and many others. So seismicity is a very clear and obvious monitoring tool for volcanoes, but there are many others. Ground deformation, whether this is GPS or tilt meters, is another, and more recently tools such as seismic tomography. This data published by Luca De Siena around 2014 is a good example, again looking at the Campi Phlegrae area, which we'll come back to towards the end. And tomography is sensitive to the fluids within the rocks. That can be a useful tool as well. And finally, geochemical indicators. Volcanology has its roots in geochemistry in many ways. So the classic geochemical gas sampling petrology is also very important. But I'm going to concentrate really on the seismic aspect in this talk. So back to the volcanic system and rock deformation. In many ways, this is the image that started it all for me in my career anyway, the backstory. I originally saw this slide at the end of a keynote talk that Steve Sparks was giving in Iceland. And as a young postdoc, I thought, well, that looks very interesting. Steve had listed a whole bunch of problems that needs to be tackled, listed on the right hand side, and many of these things were interesting to me. The coupled system problems, seismic data, rock physical processes and properties, rock mechanics. So the question then becomes, as you can see from the left, this is an extremely complicated system with heat, gas, fluids, interaction between all of those things. How do we decipher such a complex system? So the tool I've been using for this is rock physics. So this describes a relatively new geoscience discipline, integrates two more traditional ones. On the left hand side here, rock physical property measurement. So we measure the properties of a specimen, a rock, as a function of pressure or temperature, and the key thing here is that these are things that we can control compared to things in our field which we cannot control, or we can only infer from our observations. So this on the left is a classic piece of equipment known as a Patterson apparatus. This is the one, a schematic of the machine in ETH Zurich. The kind of data sets we would record from these kind of apparatus include decreasing permeability as a function of increasing effective pressure. So 100 MPa here is about 4 kilometers depth. So the permeability of this Sandstone decreases by a significant amount as we increase the pressure from surface to an equivalent of about 4 kilometers. And there's more to it here. There's anisotropy in the flow rate data, parallel to cross-bedding and normal to it. And on the bottom, more data this time, elastic wave velocity, p wave velocity, decreasing to an inflection point as we approach around 900 degrees or so, the alpha beta quartz transition, published a few years ago by myself and a former colleague. And on the right hand side, rock mechanics, the traditional rock squashing. So here's one I prepared earlier. So traditional rock squashing functions as a property of macroscopic scale. This is the machine you have in Portsmouth, a 60-ton press. In the background here, this is the machine in the experimental volcanology lab in Munich, where they fitted their press, the same kind of concept, with this blue box is a large furnace to simulate high temperatures and therefore volcanological conditions. Add all that together with equipment for microseismic location, these sensors and various electronics to record all this data as a function of time and stress and fluids, and we end up with the modern discipline of rock physics. And this is the rig here in Portsmouth, our rock physics triaxial ensemble, to record and understand how rocks respond in terms of their seismic character due to stress and fluids and rock fluid interaction. And the typical data, just to finish off this little setup, we can identify 4 distinct modes of failure, from axial splitting, A, through to a single shear fault. A bit more pressure, a bit more depth gives us a pair of conjugate shear fractures, and finally at high pressures we enter the ductile or quasi-ductile regime. These sketches are from Mervyn Patterson's classic work back in the 70s, and again here are some photos of the same, of the formed coronal lob. So we can do all these things on our volcanic system to understand a little bit more about what makes volcanoes tick. So essentially this is the answer, the tool that I've been applying to these kind of problems, and to understand in particular the different sequences of signals that are produced from active volcanoes under different conditions. So on the right hand side, to give you a little bit more background, there are many different types of seismic signals that we record on volcanoes. And going back to the 90s, even the 80s, these were started to become investigated in slightly more detail. One of many researchers was Bernard Chouet at the USGS. He wrote a review paper in 1996 in Nature, here's the link, where he summarized the different kind of signals. So we have long period or low frequency events, which are characteristically low frequency, hybrid with an element of the low frequency but also a high frequency precursor, and then at the bottom the classic volcano-tectonic event, essentially an earthquake but generated by a volcanic process as opposed to a purely tectonic process. And these can be further classified into shallow and deep and other types of generation mechanism. And there was a moment in this at this time where we thought, the community thought, that these long frequency events, low frequency events, may herald the beginning of a new era of accurate volcano eruption forecasts. The thinking being that these low frequency events occurred just before the eruption, or as you were getting close. Now that turns out not to be the case, but nonetheless it was something interesting to work on, and that's kind of where I started my career in a sense. So in the second part of the talk I'm going to tell you a little bit about how we started out doing that process of investigating what drives these different signals on active volcanoes, and where that's taken us today, because it turns out that the situation is not as clear-cut as was first thought. So these experiments were done a few years ago now. They're conducted in 2 stages. The first stage is to conduct a standard triaxial deformation experiment. You saw my prop earlier, something like this, so single shear fault. And this is monitored using a suite of those acoustic emission transducers that you saw a few slides ago. And once we've fractured, we generate this damage zone. The damage zone can be accessed by a conduit drilled through the center of the sample, which is a cylindrical sample. And in the second stage, the pore fluid saturated sample, water we use, is then rapidly released to try and stimulate rapid fluid movement and to generate, hopefully, some of these low frequency events. So stage 1, here's an example of the first stage, standard experiment with stress in black here and the volumetric strain in blue. On the right hand side, you may need to turn your volume down on your headphones if I got the setting right. If I got the setting wrong, you won't hear anything, but let's try it and see. So this is the sound of an earthquake in a laboratory using 2 channels. So you've got this in stereo. As we approach the failure, the number of fractures, the cracking increases until failure. Stand by to take cover. So assuming you can hear me still, I've not blown your eardrums away, then there are 2 important points to make about this. Interesting demonstration, first of all, of how we can listen to acoustic emission in a laboratory by slowing down the normally high sampling rate to the audible rate, in exactly the same way as seismologists take tectonic earthquakes and speed them up. They also hear the same audible fracturing noise. So it's not just a fancy demonstration for a little bit of fun. It also tells us that some of the scaling can be done in exactly the same way from the lab to the field as you can do from field back down to the lab. So that gives us some confidence that we can do these experiments and apply it to the field with a reasonable amount of robustness. So these experiments, the stage 1, just to generate a fractured damage zone, you chose representative pressures, pore fluid pressures and strain rates for the second stage of the experiment. So here's the first stage again. On the right hand side, a little animation shows each of the hypercentral locations during the formation of that single shear fault. Each of the black triangles is a receiver on the sample. So this is about 5 centimeters across, by the way, about 12 centimeters high. And it maps out the damage zone quite nicely compared to the actual sample on the left. So far so good. Part 2, as I said, with the damage zone formed and mapped out using those acoustic emission locations, we can now start to play about with the conditions required to generate low frequency events. So the idea here, the model, if you like, is that if we can stimulate rapid fluid flow through that damage zone at a sufficiently high speed, we can generate turbulence due to various pinch outs and bottlenecks and rock microstructural features, which are analogous to the kind of low frequency data we see in the field, but under controlled conditions. So in these early experiments, we released the pressure from 20 MPa to 0 very quickly and stimulating fluid flow. So the fluid flow was not completely controlled, but nonetheless it was sufficient to generate low frequency data. And it worked pretty well. So here is the result. published many years ago now, but still worth a look. You can clearly see in this map, this is an SEM map, many different panels put together. Here's the conduit down through the middle, here's the fractured damage zone with a small conjugate as well. Locating these low frequency events, so much lower frequency this time, is not as straightforward. The onset is not as clearly defined, it's more emergent, and there's not so much data, simply less data. But nonetheless, they do map out along the damage zone, and in particular, if we zoom into a couple of these example features, A and B, these are panels A and B, and sure enough, we see the kind of microstructural features that we were postulating could be a generation mechanism for low frequency events. So far so good. It was a good result. We were very happy with it. There's of course much more we can do. So summarize those experiments in one slide. Here we have the failure stage on the top. Sorry, shallow and deep volcanic tectonic events. That's what we're simulating here. On the right hand side, typical data from the acoustic emission sensors shows that high frequency. There's a low frequency component as well, but there's a lot of high frequencies here. In complete contrast to the second stage of the experiment, where we're simulating these long period or low frequency events, and sure enough, the acoustic emission data much lower frequency, and the high frequencies are more or less absent. So it worked pretty well. It is of course impossible not to make the comparison at this point with lab and field. On the left, laboratory data, on the right, field data. As you saw in the last slide, it works pretty well, and also for the volcanoes, so Pinatubo, some typical long period data, Gararas, again, all looks very similar to the kind of data we're recording in the laboratory using our fluid turbulence type model. And one of the earliest earthquakes on Etna volcano, this is on the right, bottom right, to compare with a fracturing event from a sample of Etna basalt in the lab. So same rock type, different scales, but it looks very, very similar. And most recently, now just a few years ago, my former colleague Marco Fazio was able to further elucidate what's going on by measuring the same kind of data. So we have a very long, this time tornado type event, and superimposing that on the measured pore pressure evolution at a high sampling rate. So we have different pulses of pore fluid decreasing, stimulating an event, a second pulse, and finally the third pulse of pore fluid decay, stimulating this very large quasi continuous event, which is what we often see in the field. But moving on to the data in more detail now, there's always been this challenge for the laboratory-based rock physicist in that we have sensors which are poorly calibrated as a general rule. We only record the voltage output as opposed to a well-known receiver response that you get from a seismometer. So to somewhat make up for that, this has just been recently submitted, we've been recently trying to understand the waveform in more detail depending on how it interacts with a fault zone. So I'm not going to dwell on this. This is watch this space. This paper's coming out soon in Geophysical Journal International. Tom King modelled the response of a source. So here's the source in panel B, whether it's above, within or below a fault zone, and what it might look like as received by this receiver M1 in red or M2 in blue. And the model works pretty well. This is just a model, no data at the moment, and the model works pretty well. And we're hoping in the future to use this kind of approach and to better understand the attenuation inherent in our lab scale samples as a comparison to field data. So I won't say more about that, but watch this space. Okay, so to finish part 2 of the talk, I'm going to go take it quickly to one side and talk about temperature and tensile fracture. Because all the experiments so far have shown you, all of our simulations in the laboratory, even though they work very well, and even though they are somewhat qualitative as opposed to quantitative, none of them feature high temperatures, or tensile fracture actually. And of course volcano-tectonic processes operate at high temperature. And of course they involve tensile fracture like dike injection. So the question comes immediately, can we do this in the lab? And the short answer is with great difficulty. Temperatures add a lot of complexity. The simplest way to do this is to go back to the idea of a uniaxial press. This is the one in Munich again with a furnace around it. Here the sensors, the acoustic emission sensors are located right at the top of the piston, and right down here you can just about see the cable actually behind Jan. At the bottom of the piston, to keep the sensors away from the high temperature zone, otherwise the temperature burns and destroys them. Nonetheless, it kind of works. Here's the acoustic emission response due to the fracturing of a Colima andesite from Mexico. And if you remember this example from the beginning of the talk, we have a conjugate shear fracture. This is in the brittle regime. It doesn't look completely dissimilar to the sample I'm holding just up here of the deformed, very well deformed, 75% strain or whatever, and quenched sample of Colima andesite. So maybe there is space for this kind of experiment. So off he went, attempting to do some high temperature fracture mechanics experiments using volcanic rocks at high temperatures and in tension. And it took us several attempts. So in this first attempt, rather uncontrolled, but it proved the concept of pressurizing a core in black here, and as the tensile fracture moved out radially, we can recover some sort of acoustic emission, and on the right hand side sort of looked like at the end. So it didn't work very well. The high temperatures are a problem, huge challenge. So eventually abandoning this and moving to a proxy material, so PMMA, simple plexiglass, perspex, which was found to be a very versatile substitute. And this time, deforming the molten or semi-molten plexiglass, we only require around 200 degrees, whereas the last slide we require something like 800, 900 degrees, and this is far more controllable. So this was published 2016 or so, and now we can see quite clearly, once quenched, the plexiglass core, when it's fracturing, it pressurized, fractures an outer shell, and then solidified into a proxy for some sort of dike injection. So this works much better. And you're probably thinking, why am I telling you all of this? Why am I going all the way out now to simulations of tensile fracture? Well, it's because during these experiments, although the plastic PMMA acts as a pretty good proxy, we still noticed, so this is the experiment here on the left hand side, here's the pressurization of the conduit in green, and it got to a maximum just at the time we see a huge rise in the acoustic emission events, so i.e. the fracturing, tensile fracturing. And if you locate in a Rose diagram the acoustic emission, it matches very nicely in plan view with the radial fracturing. So nice result. But we also noticed that there was still evidence of low frequency data in the acoustic emission waveforms. So here we have before failure, before the fracturing event, about 900 seconds, so that was measured just before the big fracturing event. A lot of high frequencies, sharp onset, somewhat like a VT type event, Whereas after failure, we have this resonance and lower frequency component. But of course there's no fluid here, there's no water, I should say. The PMMA is very viscous. So it may be, in fact, that this model that we used in the previous set of experiments is not necessarily required to generate low frequency data in the lab, at least. So that got us thinking, could there be another mechanism out there for generating low frequency and LP data? And we weren't alone in that thought. So that brings me nicely to the third part of the talk, and final part of the talk, the new paper and the new results. Because we were not alone in noticing this. I was talking at a conference in real life once upon a time when we used to do those, with Chris Bean, who had also recently published, so this is in 2013, the experiments on the previous slide is 2016, so we just published those, and I bumped into Chris Bean at the conference, and he'd just published a model. He had noticed that his model could, under certain conditions of low strain rate or slow eruption velocity, produce a wave field very similar to long period or low frequency data. So on the right hand side, these are some typical models that his computations would spit out. A sequence of these pulse-like long period events near summit stations. So it got us thinking, could we do something similar? So we teamed up to try and test this idea. So this is the work again of Chris Bean. So his early models were very interesting, very intriguing. So the top model here is the slow rupture seismogram caused by, as I've written here, by a 500 meter long vertical crack. So here we have a seismogram. On the bottom, the rupture velocity is very slow, 800 meters per second, much lower than you normally anticipate. To get that kind of data, a material is needed with extremely low cohesion, or a very, very weak rock. And the model that you saw on the previous slide suggested something with a cohesion of 2.5 MPa. So here we have the strength tops out at about 2.5 MPa, and we see a number of events. This is all from one model this time. This is not lab data, this is from his model required to generate the data from the previous slide. So to test this kind of model from Chris Bean, there does happen to be a very suitable rock type going all the way back to the beginning of the talk, returning now to the Campo Flegrei area. So Naples is here. This map is just on the left of Naples, so Campo Flegrei area, and in particular the Neapolitan, the classic Neapolitan yellow tuff, which happens to be a very low strength volcanic rock. Ideal for testing Chris Bean's model. Here's what it looks like in the quarry. Just to prove I do occasionally go to the field and collect rocks myself. So here I am, selecting some rocks from the quarry face. It's used as a building stone. It's very common in the Naples area. Here's another outcrop. Plenty of volcanic products in this area, as you can imagine. And it was this material that we collected and did some experiments with. Sure enough, it's extremely weak and extremely porous, around 30% porosity, and not very strong as well. So some experiments, here we see the material after they come down to the Traxel machine, just about holding together, generating VT events during the experiment, as we often do. And on the right hand side, here's a sequence of experiments, all showing the same kind of trend, maximum strength around 8 megapascals, and with the character very, very similar, almost identical to the type of material that Chris Bean's model required to generate low frequency data. So far it's a good candidate material, and this is the one that we then used to generate to generate some data. But there are some problems. This is such a weak, low porosity material that it's very difficult to locate acoustic emission in detail. So one of the few experiments that worked was this one. So you can see the fault zone, and here are some acoustic emission locations. But nonetheless, we persevered. And we persevered because in all the experiments we got this persistent tremor at a far lower frequency range that we would normally get in a more competent rock like the Etna basalt you saw earlier. So around 100 or 200 kilohertz in Neapolitan tuff compared to the normal, I want to call it normal, AE type data from the competent Etna basalt. So far it looks very interesting, and it's very important actually. And why is weak rock important? Because the forecast I showed you briefly before from Chris Kilburn's model, it's another more recent study of Chris Kilburn's, suggests that there are different transitions in the volcano-tectonic rate data as we go from a hyperbolic increase to some sort of transition, that's the star in each of these different cases, to some sort of linear phase. And Chris is postulating in some of his recent work that this is because we move from a brittle, purely brittle type of process, such as Etna basalt, let's say, to some sort of plastic or quasi-plastic process once we get to some sort of geophysical threshold. Whether that's in this case horizontal displacement or uplift or tilt. And weak rocks tend to favour this plastic process of deformation, so it could be very important. And we see this is consistent with some field data. So it's very important, and I'm happy to say that the new results we got after many experiments, and I'm not joking when I say many experiments. So Pete Rowley, this is data of Pete Rowley that we published just last year. I think we did something like, in numbers, something like 30 experiments generating something like 28 terabytes of data before we got the procedure to run nicely and consistently. And what we found here is a nice comparison between field data, again, with no fluid, long period events, and our experiments, again, now with no fluid, just a weak, low cohesion material, the Neapolitan tuff, generating the same kind of long period, low frequency data that we previously thought was exclusive to fluid-driven rock-fluid interaction. So clearly there's a lot more to this story. What could be the mechanism? And it's still somewhat elusive, but the lab data suggested that the strain rate is the key control here. At high strain rates, the data continues only for a short time after the peak stress, the strength is reached, whereas at low strain rates, we generate this quasi-continuous signal, and it only ends when the machine runs out of data recording capacity. Backing that up with post-test X-ray CT confirms this kind of idea that these quasi-continuous ductile processes are generating low-frequency events and in a quasi-continuous process. So these look the same. A is before deformation, B is after deformation. It's only when you subtract B from A and do a difference analysis you can just about see the deformation is picked up just around the different pore spaces and grains of the Neapolitan yellow tuff, suggesting that this is a plastic process around these microstructural features. Just about on time, so I'll talk through our general conclusions and thoughts. Over the last 15 years now, maybe even 20 years, laboratory rock physics has been used in some great detail now to understand different volcanic seismic sequences. So VT events, generally thought to be generated by brittle fracture. They're strongly influenced by scattering and geometrical effects though. And although water resonating through fraction damaged zones can generate low frequency or long period, depending on where you're coming from, different backgrounds, we use different technology. Due to turbulence, there are definitely other mechanisms capable of generating these signals. And it's that has resulted in this idea that low frequency events is the new panacea for forecasting, has been knocked into the long grass somewhat. Because one such option is to use low cohesion materials and does not require water. So strain rate, we think it plays an important role here, but there is this important caveat: we still need some more data. The 28 terabytes, alas, may not be enough still. Processing such large data sets is a huge problem. Hopefully artificial intelligence and machine learning is going to be our next solution to processing the data from these huge data sets. And also in the future, hopefully working with folk just wanting to understand more about forecasting. So there's lots to do, lots of school rock squashing to do. Good clean fun. Before I sign off, I just need to thank and acknowledge all the group members listed here, past and present. It's very much a team effort. Rock physics, especially these kind of experiments which take such a long time and with such a lot of data. So I will stop there. Thank you very much.
Thank you so much, Phil. I'm just going to bring us all back there.
As my voice starts.
Do you have some water with you?
I don't, actually.
It's unfortunate. If anybody has any questions, please feel free to put them in the chat or the Q&A box. We'll be monitoring both. And feel free to congratulate Phil on a lot of great work over the years. I had a quick question, which I feel like I may have been imagining this, but in your second to last slide with the rock deformation differencing, is there a faint sort of plus sign through the middle? They're like a dark plus sign. Am I imagining that?
Maybe. Maybe not. I don't know. There's a few other features here as well.
Yeah. Did you investigate those, or do they mean anything? I have no idea.
I'm going to be honest. No, we didn't, and I've no idea.
Great.
Who knows?
I thought that might be the answer.
Yeah, who knows? I didn't particularly notice it before, but it's an interesting question. I'm not sure is the honest answer.
Nope, fair enough.
Hopefully it's just a process, or maybe it's just a processing artifact. It looks too regular to be anything natural, but who can say? Yeah,
cool. I did think it was a bit regular, but thought I'd ask anyway, just in case it was some sort of magical feature. Cool. We've got a handful of questions coming in, so I'll just read them out there in the Q&A box and the chat box. So Chiara Montigna, apologies for all my pronunciation, says, very interesting, thanks very much. I was wondering, how do you scale experiments to natural sizes? Are there any relevant A-dimensional numbers? Are you able to make any quantitative comparison between synthetic and measured waveforms?
Yes. Well, the answer is yes and no, I'm afraid. It's a good question, and it's one which we get an awful lot. So the classic scaling relationship goes back to the work of Kito Aki back in the 60s, and he proposed I don't have a slide, I'm afraid, to demonstrate this, but he proposed a very simple scaling relationship where the size of the fracture generates lower frequency data, and this ratio between fracture length, let's say, keep it simple, fracture length divided by the frequency that you measure, it has a certain ratio. about 10 to the 6, let's say. So you've got kilometer scale fractures, and you've got hertz scale frequency data. So you can take this ratio, and if you do that, you get 10 to the 6 or something. Then apply that to field lab data, and it turns out you get exactly the same ratio. And that is the kind of approach that is often used. I did it myself some years ago. It works pretty well, and others have tried this idea as well to their data sets. I think Luigi Bellini, another well-known, who passed away some years ago, used to run in the lab in Zurich. He did the same for some of his work back in the day. So that's kind of how we've approached the scaling problem. But you're right, we don't have sensors which are calibrated in absolute terms so much. That is changing. There's new technology and new sensors where we have a faceplate calibrated for velocity, but most of the AE data is uncalibrated voltage, and therefore we have this qualitative comparison is more common than the quantitative comparison. But I guess watch this space again. Things are slowly starting to change as the technology improves.
Cool, thank you so much. Hopefully that answered their question. Mike Cassidy has asked, hi Phil, nice talk. In the future, do you think we can calibrate the approach to detect strain rates from seismicity if we know the type of country rock?
Yes, I think so. I think it would be great to, I'm just reading a comment on the computer. Yeah, strain rates from seismicity. Yeah, it would be great to try it. I'm not precisely sure how yet. I think the future may lie in some of these optical fiber strain meters, which are starting to become more popular again as things get cheaper, and I see there's been deployments actually on Stromboli recently. And that kind of really dense strain meter data, I think, will be needed to generate enough data, and then relate that to different strain rates, which you can then take those from GPS and other measurements to see if there's a correlation there. But I certainly think it's worth a try.
Cool, thank you. Mark Thomas has asked, hi Phil, for this.
Hi.
For the slow rupture model, how repeatable is this? Can you continue to slow rupture the same area to keep the source stationary?
Yeah, it's one of those things we didn't get a chance to finish, I'm afraid. We would like to have done more strain rates and keep getting slower and slower, but then you run into problems of generating enormous data sets, and the machines really don't like being run too slowly. You start running into stability problems. So typically an experiment can take an hour, and then you need to do one that takes a day to go to like 10 to the 6 strain rate, and then to go 10 to the 7 it's going to take a week. Keeping a machine running for a week consistently without going wrong is already difficult, and then you go to a month and you move to the creep regime, and this was a problem that we found. So we would like to have done more experiments, but we didn't manage it, I'm afraid. I would like to think, to answer your question, that it is repeatable enough and we can continue to do it, but we just didn't manage to get the data set yet to prove it. I'm hoping maybe with some more work with synthetic rocks would be easier than using the Neapolitan tuff. So sand and cement mixtures of known cohesion. Calibrated cohesion could be the way forward. Or I could talk to you about doing particle flow code maybe. I hear you're the boss of particle flow code.
Maybe a good follow-up email. Great time to start a collaboration. Mark has said in the comment box, "Ooh, I wish."
I wish, yes.
There are a handful of questions in the chat section. Itahisa Gonzalez has asked, is there a preprint available for the King et al. Paper he mentioned, the one submitted to GJI?
Yeah, I'm afraid not, actually. We didn't get around to doing that, or rather Tom didn't.
Yeah.
That was one of these Herculean efforts after he finished his PhD, and after many months we finally got it submitted. It's come back now with positive reviews, so it should be coming out soon, but I'm afraid there's no preprint. We didn't do that this time.
Cool. So watch this space, hopefully out
Watch
soon.
this space. Watch this space, or check out ResearchGate. Maybe Tom has been naughty. You never know. Or Sergio has been naughty. Is more likely, actually.
And there's a question from John Sticks here saying, thank you for a very interesting talk. For your dry, low rock strength model, can you say something about accumulating pressure conditions in and around the crack?
That's actually difficult. I'm just reading your comment again. Yes, accumulating pressure conditions in and around the crack. I suspect there aren't any. Because for this low cohesion, low strength model, somewhat really relating to Chris Bean's work, it's such a high porosity sample, I don't really think there is a pressure buildup. It's more likely that you've got some sort of fluid induced weakening that's generating a transient energy that we then record as a low frequency data. But this is just me speculating, really. It would require a lot more work.
Cool. Well, I hope that answers that question. Yeah.
Possibly not.
They say thank you.
Oh,
so
more discussion required. But cheers, John. Yeah.
It sounds like there are some exciting questions and advances coming in this space.
Yeah, that's always the best way. It's always nice to have better, fresher questions. It's very, very soul destroying sometimes, but it's nice to.
Well, there's no more questions in the chat boxes at the moment. If you have any, feel free to quickly get them in. But we are nearing 5 o'clock. Oh, sorry, somebody raised their hand, but I don't see it there at the moment. So if you have a question, feel free to put it in, but I think maybe it was just an applause. Cool. Well, thank you so much, Phil, for giving this wonderful talk today. It's been a pleasure hosting you. Thank you for putting it together and telling us about your work.
Likewise, cheers tomorrow, and cheers everyone. Meet you in person next time.